of this mini course. So last time what have we done before? Lecture 1, we constructed the action of a two-dimensional Artin group on its Deligne complex, which turns out to be a nice cat-zero complex. Episode 2, we saw our main tool, thanks a lot, to construct lots of free subgroups in our Artin group, which is having two elliptic elements with disjoint fixed point sets. Okay. Not only that, so we can find powers that generate F2, but on top of that, and we're gonna need that, this subgroup also contains loxodromic elements. And so today we're finally gonna prove the Tits alternative for these Artin groups. I'm just gonna start with a small interlude with more something I wanted to talk last time, but I didn't have time. More free subgroups, or like free subgroups everywhere. So this theorem tells you that if you take some nice elliptic elements, you can find large powers that generate F2. Actually, we have the following result. So assume that A gamma is of extra large type. So all labels are at least 4. So for instance, let's look at the second Artin group we're allowed to look at, 4, 4, 4. Pick 2 elements in A gamma. Then there exists n such that the subgroup generated by A to the n and B to the n is either free or 3 abelian. So that sort of result that we proved before is not true just for elliptic elements, in which case you get F2, but you can get, so 3 z square, or 1 if you picked twice the identity element. That's kind of boring. Right, so it's, I mean, personally I find that really, really striking. So we know that the subgroups generated by 2 elements can be quite wild. But up to taking large powers, there's some sort of taming phenomenon that appears that I found quite pretty. So that's related to a question of Danny Wise, who asked essentially this. So in a thing that was formulated for cat-zero or biautomatic, but let's be a bit more general and just say non-positively curved in any sort of reasonable sense. Take A, B group G. Take A and B 2 elements of your group. Does there exist n such that A to the n, B to the n generate a free or 3 abelian subgroup? The question that I find really, really nice, and it's striking that there's not more known about this. So the answer is unfortunately no in general. So Artin groups are nice. I hope that I've convinced you of that already by now. Not every group is as nice, even in the cat-zero world. So for instance, so no. For instance, there's a recent example of Leary and Minasayan. So they recently constructed a cat-zero but non-biautomatic group. And it also turns out that this group is a counterexample to this question. It's not related to this property, but it's an additional result that they prove. Okay, so the original question of Wise was, do non-positively curved groups satisfy this property? It's not true in general, so we're going to change that. Which non-positively curved groups satisfy this? So there's some known results already. For instance, there's a result of Bowdish, not Bowdish, Bowdish. Don't know how to pronounce that. I think it's 81, which is a result that I learned about very recently, and I find absolutely amazing. In a RAG, a right-angle Artin group, 2 elements either commute or generate F2. So in a RAG, you can even take n equals 1. So it's absolutely, I mean, I find that absolutely amazing. That's true. Okay, so there's that. What's another result that is known? It's also true, for instance, for mapping class groups. The answer is yes, and this is due to Kuberda plus Bowdish. Because Kuberda proved that if you take two elements in a mapping class group, there's maybe, I can't remember exactly, there's maybe like the non-exceptional mapping class groups, but let's say in a mapping class group, if you take two elements, then you can find powers, large powers, that live in a RAG subgroup. That a to the n and b to the n lives inside a RAG subgroup. So a subgroup of your mapping class group that is isomorphic to a RAG. And now you can just apply Bowdish's result to conclude. So there were already kind of some results known up to using that nice result of Bowdish. So extra large type Artin groups are a new class. So you can ask yourself, what's your favorite group? Does it satisfy something like this? We've got some ongoing work with Mark Hagen where we prove that for more Artin groups and other groups via their actions on trees. But I find that question really nice. And so we've just coined that property, the y is power alternative. And I think it's a nice question to look at. So just to advertise that a bit. Right, back to the Tits alternative. So another alternative. So how are we finally going to prove the Tits alternative? So we're going to prove a sort of a kind of classification of subgroups of a two-dimensional Artin group. So H, a subgroup of two-dimensional Artin group. No assumption of finite generation, any subgroup. Then we are in one of these situations. H contains, so case one, H contains two elliptics with disjoint fixed point sets. So the case we were in the previous lecture, which already tells us that we're going to be able to construct some free subgroups. Case two, H is what's called purely loxodromic. So every non-trivial element is going to act loxodromically, which I guess is equivalent in that case to H being H acts freely since the group is torsion free. So every element in H different from the identity is loxodromic. The third case is H fixes a vertex, so kind of elliptic, globally elliptic of the Deligne complex. And there's a fourth case, H globally, so stabilizes, so not fixes, stabilizes, so globally, what's called a standard tree, so which is one of these fixed point sets when G is a conjugate of a generator. So the case where the fixed point set is not a single vertex, but a possibly more complicated tree, and sometimes even an unbounded tree. So there's that kind of, that's not a dichotomy or trichotomy, and I don't know how to say it for four. So classification with four classes, let's just keep it at that. And so I'm gonna show you how to prove something like this, but maybe before that, let's see how this classification implies the Tits alternative. So I just change. Right, so we just need to treat each of these cases. So case one, well, lecture 2, and that's actually recalled above, implies that there exists a copy of F2 inside H. So there's nothing to do here. Case 2, so case 2 is quite hard. I don't know how to prove it with just kind of Deligne complex sort of arguments. We would quite like to, but thankfully, there are very clever people who can deal with a situation like this. In particular, there's a result of Damian Ozaida and Piotr Przytycki, who proved the Tits alternative for groups acting freely, or almost freely, but let's say freely, on a cat0 two-dimensional complex with finitely with, in our case, finitely many isometry types of simplices, and actually more general result, where they prove the Tits alternative in that case. And we can apply their results kind of on the nose for our subgroup. So consequence, so follows Ozaida, Przytycki. Part 3. Okay, so now we need to understand, so what happens if H fixes a vertex? So it means that H is contained in a vertex stabilizer. Thankfully, because of the construction of the Deligne complex, we know exactly what the vertex stabilizers are. The vertex stabilizers in dimension 2 are either trivial if we have a type 1 vertex, Z if we have a type 2, a type 1 vertex, and what we call kind of dihedral Artin group otherwise. Okay, so well, the first two cases are okay. They clearly satisfy the Tits alternative. But what about dihedral? So dihedral as well. And that follows, for instance, from, well, if you go back to the first problem sheet, so one of the exercises was about understanding the structure of the dihedral Artin groups, and in particular, in problem sheet 1, it was proved that, right, so if the coefficient is 2, we just have a z square, so that one is easy, so we're just going to assume that MAV is at least 3. The quotient, the central quotient of my dihedral Artin group is actually a free product of 2 cyclic groups, and more precisely, it was Z star Z M over 2 if M is even, and Z mod 2 star Z mod N M if M is odd, where M is this MAB. So it's a free product of 2 cyclic groups. So in particular, this thing here is virtually free, which, with a bit of abstract algebra, tells us that my dihedral Artin group is virtually Z cross free. And now, in particular, this satisfies the Tits alternative. The Tits alternative is stable under taking direct product, and it's stable under taking supergroups of finite index. So we're good. Okay, is that bit clear for everyone? Okay, so that was for part 3. Part 4. So part 4, there's a bit more work. We need to understand what the stabilizer of one of these 3 fixed point sets is like. So I'm just gonna take fix of A, where A is one of the standard generators, so really corresponds to one of the vertices of my presentation graph gamma. What you can prove, which is not very difficult, is that the stabilizer of this thing is exactly the centralizer in A gamma of my element. So there's one inclusion that is clear. If you have an element that centralizes A, is going to preserve the fixed point set of A. It's just a bit of kind of abstract nonsense playing around with what this means. The other inclusion requires a tiny bit more work, but let's just admit it for now. So the good news is, it means in particular that, well, there's a nice description, and on top of that, so the stabilizer of fix A acts on fix A, and fix A is a tree. And actions on trees are nice, and we like actions on trees. Everyone loves Basser's theory, or everyone should. So we can try to use Basser theory to kind of understand this group here. So, so the first thing to notice is that inside the centralizer of A, the subgroup generated by A itself acts trivially. This is almost, well, this is by definition, because fix of A is all the points that are fixed by A. So A acts trivially on this. So instead of looking at the center, so this group acting on the tree, you can just look at the quotient to have something that is going to be hopefully faithful, and it is faithful. So let's look at C of A mod A acting on the fixed point set. So you have your what we call standard tree, and you have the action of that quotient C of A modulo A. So because the stabilizer of every edge in that tree had exactly that group as a stabilizer, the stabilizers of edges are now trivial. Okay, so with a bit of Basser theory that tells us essentially that this group is going to be a free product of some of the vertex stabilizers that appear in the picture. So we need to understand the vertex stabilizer for this action. So I'm just going to look at one case, say VAB inside this standard tree. So the picture, if I have it here, if this is the edge stabilized by A, so this edge is in my fixed point set, and I'm looking, for instance, at that point VAB here that corresponds to the hedral Artin group generated by A and B. The stabilizer of that vertex for this action, so we have to be a bit careful. It's a little exercise to check that it's the centralizer inside the dihedral Artin group of the generator. But that, if you go back to the problem sheet 1, we computed this. This is exactly the subgroup generated by A itself and the central element of AB. So actually, since I'm looking at the action of the quotient, it's modulo A and modulo A. So in particular, it's this thing. So bottom line, this group here that I'm trying to understand, or its quotient modulo A, acts on a tree with trivial stabilizers and Z vertex stabilizers. And now by Basser theory, that just tells you that this quotient is free. A bit more work, you can show that it's finitely generated and free, but doesn't matter here. And so now this shows that C of A is isomorphic to Z cross 3. And again, in that case, we know the Tits alternative. So we had our 4 cases. The slightly more involved one, well, no, actually 2 is really involved, but the geometrically involved one were 3 and 4. So stabilizers of vertices or stabilizers of trees. In one case, we're virtually Z mod free, Z times 3, so we're good. In the other case, we're like really Z times 3, so the Tits alternative follows as well in that case. Okay, right. So now how do we prove something like this? And before I do that, how much time do I have? Let's see how hand wavy I need to be.
23 minutes.
All right. Okay. No, this might actually have early coffee. Okay. Good. No, maybe not here. So how do we prove the classification theorem? So it's good that I haven't erased it yet. Or a classification proposition, because you'll see that it's not difficult. Essentially, you've got all the tools to prove it now. So we've said, so we're going to take our subgroup of A gamma, and we're going to try to show that it satisfies one of these four conditions. So we know that in, so a given element of A gamma either acts elliptically or loxodromically on the Deligne complex, right? So we're going to look at different cases. So we're going to say that a subgroup H of gamma is so purely loxodromic if, well, we've already seen the definition, every H non-trivial is loxodromic. So there's kind of the relative notion of purely elliptic, but now the terminology seems to be locally elliptic. So let's use that instead. Locally elliptic if every element is elliptic for that action. So in particular, every element has a fixed point. And finally, well, the other case, we're just going to call that mixed. Otherwise, if there's at least one loxodromic and at least one non-trivial element with a fixed point. Okay, so we've got those three cases, and we're gonna show that in each case we satisfy one of these. Okay. Oh, there's one case that is easy. It's that one, so we're gonna skip that one directly. We're actually gonna look at mixed first, because I'm gonna need a lemma from there for locally elliptic. So, well, I used 1, 2, 3, 4. So case A, let's say here A, B, and C. So let's start with C. So we're mixed. So we've got at least one loxodromic element. So let's call it H. And we've got at least one elliptic element. So we know that also from lecture 2, we know that elliptic elements come in two flavors: vertex elliptic, where the fixed point set is a single vertex, or tree elliptic, where the fixed point set is like a more complicated, what we call standard tree. So first case, if there exists a G in H with fix of G is a single vertex, then we're good, right? What do? So we've got our element G that stabilizes that vertex here. If I conjugate by G, I get an elliptic element that stabilizes that vertex here. So here I've got G. If I conjugate by H, I've got this element here that fixes H V. And these vertices are really the fixed point sets. Fix of G, and that's fix of H, G, H inverse, which is also in H. So what we've done, we've constructed two elements of my subgroup that are elliptic with disjoint fixed point sets. So we are exactly in case 1. And so we're good. This is case 1 of the classification theorem. So that was the case where we had at least one vertex type elliptic. So let's see what happens if that's not the case. So now we can assume that all elliptic elements are of tree type. So their fixed point set is a standard tree. And here I'm going to use so let's first do the same thing. So let's now assume all elliptic in H are essentially of tree type, which by the result from last time means that they are conjugated to a generator or a power of a generator. The picture to have in mind is I've got my fixed point set, which this time looks like this. And I've got a loxodromic element, so there are different cases. If I do the same trick, so I conjugate, so this means translating my fixed point set by the element h. If now those trees are disjoint, we're good. We're exactly in the same situation where we have two elliptic elements with the disjoint fixed point sets, so we can apply the F2 subgroup proposition from last time. There's a second case that we need to look at. What happens if by applying H, we obtain two disjoint standard trees, but they meet, something like this. Okay, so this is a possibility that we need to account for. So it's a standard result about these trees that they're going to intersect at a single vertex, actually of type 2. So up to conjugation, we can assume that that vertex is, say, that vertex corresponding to the dihedral subgroup VAB. So it means in particular that my two elements here, so let's call that one G prime. So I've got fix of G prime. They intersect at that vertex here. So by definition, this means that G is conjugated to either a power of A or B, and G prime is conjugated to either a power of A or B, just by what it means to be of tree type. So G so it's conjugated to I need too many so S, X, S inverse, and G prime is T, YM, T inverse, where S and T, X and Y are either A or B. Right? It's kind of an annoying way to just say G and G prime are conjugated to powers of my generators A or B. And so what I'm going to do out of this, I'm going to construct a new element, an elliptic element whose fixed point set is exactly a vertex. And I'll be back to that case here where I had a loxodromic element and an elliptic with a vertex fixed point set. And so being a vertex fixed point set means not being conjugated to a standard generator, right? And if you remember what we've done in the exercise session just before, there's kind of an easy way to kind of guarantee that something is not going to be conjugated to a generator. What is that? It was kind of the little trick I used to construct some elements that were guaranteed not to be conjugated to generators for one of the exercises. Is to, sorry? So, well, it's not loxodromic because I want something that is elliptic. Yes, they map, so they have height 0. If I can force the height to be 0, this is essentially going to tell me that they have to be trivial if they're conjugated to a generator. So how do I do this? Well, I'm just going to look at, take my new element, G second, which is G to the M and G prime to the minus N. Okay, so the height of that thing by construction is 0, and that's still an element of H. So if G second were of tree type, so were conjugated to a power of A or B, the only possible way would be power 0. So it would mean in particular that G to the M would be equal to G prime to the N. Then G to the N has to be equal to G prime to the, no, G to the M has to be equal to G prime to the N. So in particular, their fixed point sets have to agree. But I mentioned last time that the fixed point sets always behave extremely nicely, and taking power doesn't change anything. So actually that tells us that G and G prime were already the same standard tree. So I was actually not in that situation here. So that gives me a contradiction. So contradiction, assuming that they are assumed to be distinct here.
Right, can you just go over what we need the answer? You said that if you couldn't find second MN to make the height 0.
So we can always find that M and N that make the height 0. That tells us that this element cannot be equal to the identity, otherwise we would have this equality that is ruled out. And so that tells us that G second has to be of vertex type. So its fixed point set has to be that single vertex at the intersection between the two. And so now we're back to the previous situation, back to loxodromic plus vertex type, which is the picture we had before, which is that one. And the last case, so I've assumed here that I had a way to, by looking at my elements, I get two distinct, I've got essentially elements in H with fixed point sets that are trees, but distinct trees. The only left case that I had to, that I have to look at, final case, all elliptics in H have are of tree type and have the same tree. So the same fixed point set tree. But that precisely means now, so let's call that T. That precisely means now that every element of my group is going to have to stabilize that tree. Because if I conjugate an element with fixed point set, this tree T, if I conjugate it, I'm going to have an element whose fixed point set is GT, but that has to be the same T. So that precisely tells me that my element, so stabilize T. And now we are in the case where H is in the stabilizer of a standard tree, which was case 4. So if we kind of summarize what we've done in case C, so we were in the mixed case where we had at least one loxodromic, one elliptic. Either we're going to be in the situation where we can construct two elliptic with disjoint fixed point sets, in which case we can construct F2, or we're going to show that our subgroup actually is contained in the stabilizer of one of these standard trees. Okay, and I've got 7 minutes. Is that correct? Or yeah. Yes, so just enough time. So let's look at the locally locally elliptic case now. We've done that. What can I erase? I'm gonna start here. Okay, so case B is the locally elliptic case. And what we want to show, and that's kind of related to the sort of the types of questions I mentioned on Tuesday, we want to show that locally elliptic implies globally elliptic. So if every element fixes a point, then the whole group fixes a point, right? Which is a nice type of result. Actually, so there's again like a deep result of Damian and Piotr when they, is it also with the study article with Norin, or yeah, so Norin, Ozaida and Przititsky, where they proved that torsion groups cannot act without fixed points on, let's say, cat-0 two-dimensional complexes. But you can use in that case, it doesn't work for all two-dimensional complexes, but the Deligne complex has nice angles and their machinery works. But it's a deep result, it's a difficult result. And here we really have lots of tools to kind of prove that in a rather elementary way. So like in French, like using their result would be called kind of using a jackhammer to kill a fly. So instead we're almost there. So we're gonna be a bit more elementary. Yes, a jackhammer if you're really French. So, okay. Or I can start here. Right, so by assumption, everything is elliptic, right? So everything has a fixed point. Right, So first remark, if I take any x and y in H, then necessarily their fixed point intersect. Okay, why is that? Because otherwise we would be in the case where these elements are elliptic, they have disjoint fixed point sets, and by the results that has now disappeared from last time, we can construct by taking large power some subgroup that is F2, not the important bit, which contains loxodromic elements, and that's the key thing. So otherwise, we can construct loxodromic elements using the key proposition from lecture 2. Okay, so let's continue. So again, we're going to look at the various possibilities for the types of fixed point sets. So again, the fixed point sets can either be a single vertex or one of these standard trees when you're conjugated to a standard generator or a power. So if one of them, if there exists x in H with of vertex type, where so the fixed point set of x is a single vertex, then by this remark, this means that every element in H has to fix that vertex, right? Because this unique vertex also has to be in the fixed point set of every other element y by this remark. So we're in the case where then every y in H fixes V by, let's call this equality here, star and star. So we get that H is contained in the stabilizer of V, and we're back to something that was in the classification, that's case 3. So we're good. So now we just have to, again, look at what happens if we're not in that situation. So if all elements in my, if everything is of tree type, x in H are of tree type. Okay, so if you take x, y, 2 elements in H, and you look at what their corresponding trees are, there are essentially 3 possible cases. The trees are disjoint, the tree intersect non-trivially, the tree are equal. Okay, and essentially 2 of these 3 cannot happen. So let's picture here. So up. So fix of x and fix of y cannot be disjoint. That's just restated, but that's just writing down condition star, right? Because we cannot contain loxodromic, so this is ruled out. Okay. Fix x and fix y cannot be a single vertex, because if we are in the situation where we have 2 standard trees that intersect along a single vertex, we could go back to something that I've just erased, unfortunately, I think. Yes, but I've just erased, which was if I have 2 standard trees that intersect with a single vertex, by taking those powers n and m, I was able to construct an element that was a vertex type, and by assumption that was ruled out. Construct z in H of vertex type, right? Where z was a x to the m, y to the minus n for the correct choices of m and n.
It's that on the top right.
Oh, no, it is there. Yeah, thanks a lot. It is here. That's that bit here. Yay. The end is erased, but that's that part of the argument. So if we were in that situation, we would be able to construct an element of vertex type, but we put ourselves precisely in the case where there's no element of vertex type, because we can already deal with the case of having elements of vertex type. So the only possibility left is that actually, again, all elements of H have the same tree, which now implies that H is actually contained in the stabilizer of any edge of that tree. So that last bit is actually slightly cheating here. It's actually not completely trivial. It means that every element of my subgroup has that standard tree as the fixed point sets, which means in particular that they each stabilize some vertex, but there could happen, something like in the bastard tree of a Bams-like solitar, where you have lines where the stabilizers of edges are Z, but they get like smaller and smaller. You get Z, then 2Z, and 4Z, 8Z, etc. Here, this cannot happen because in the Deligne complex, the stabilizers of edges is kind of all or nothing. They either intersect trivially or they're exactly the same. So here we can really say that H is contained in the stabilizer of that edge. So we're good. We're in the case where we fix something in the tree. So in the Deligne complex. So we reduced ourselves to one of the four cases. So we've proved the classification theorem. We've proved that the classification theorem implies the Tits alternative. So we have the Tits alternative. Yes.
In the lower right, like one more down, nope, one up. Well, one more up than that. There you go. Now go slightly to the right. Should that be equals?
Right. Okay. So yes, maybe not written. So it cannot be otherwise. So I guess yes. It's okay. Up. This would imply it's possible to construct something of vertex type, which is was ruled out by assumption. Yeah. Thanks. It was not very clear. Okay. So we essentially now have the full proof. Yeah. Oh yeah, of course. Yeah. Why am I? Yes.
Although I mean, in that proof of the Tits alternative, when you like your fourth application, I'm assuming an acts non-abelian tree.
Sorry, say that again.
You like in the proof of Tits from foreign application, we're assuming that it doesn't act abelian on the tree.
That H in that case here.
Yeah.
What about
you see the Tits alternative? It's fixed on the nose.
Yes. So yes. So I mean those cases are not disjoint. Yes, but yeah. So it's really an inclusion, right? So it's not. So it might be that like for instance the subgroup represented by A acts trivially on the tree, but you still have the inclusion that H is contained in the stabilizer of the tree, and the kind of the trivially acting part was taken care of when we computed the stabilizer. Okay, so I guess I can just stop here. Thank you.
Are there any last questions?
Yeah, actually.
Yeah.
So when we're doing this faster business, my question is, can you say some words about why the action is without inversions?
Yes. So the action is without inversion you mean on the tree?
On the tree.
It's without inversion on the tree because the action of the whole group on the Deligne complex is without inversion. And the reason for this, A gamma acts on the Deligne complex without inversion. And the reason for this is that if you look at the simplices were essentially, well, let's just look at triangles to make it simple. The triangles were essentially up to an element of the group. They're encoded by chains of inclusions. So they corresponded to A empty set, A, B. And so in particular, these ones are in different orbits. There's something to check. There's kind of van der Leyen underneath, but these things are in different orbits. In particular, that implies that the action is without inversion.
There is no bad question. Let's thank Alex for its entire thought.